said last time, it's kind of a segue lecture. It's going to transition us from momentum to forces. Okay? It's going to be only 2 classes. Today and on, what would that be? Monday, when we do an egg drop. Is anyone here deathly allergic to eggs?
People are allergic to eggs.
Really? No. Okay. Well, if you're afraid of them, then I can't help you. But we will be doing an egg drop, and it has to do with what we're doing here. And I'll explain the egg drop when we get to it. You don't have to bring anything in. All right. Before we talk about impulse, though, we have to talk about force, because it'll be in the formula. So we're going to talk about force in much more detail in a couple classes from now. However, you just want to know that the units for force are newtons. And we all know what it's named after, the units?
Fig Newton.
The Fig Newton, exactly. Or Isaac, yes. Okay, also, 1 Newton is really equal to 1 kilogram meter per second squared. So if 1 Newton, the unit for force, is equal to a kilogram times a meter per second squared, what could that maybe tell you about the formula for force? You have a kilogram and a meter per second squared. What are those the units for? Momentum. No. What are kilograms the units for? Mass. What are meters per second squared the units for? Meters per second squared. Acceleration. So, that automatically is actually telling you that force equals mass times acceleration. F equals ma. Okay. Yes. And Chris Campbell over here has been telling you all year that F equals ma. We're going into that next time. But okay.
That is so funny.
But we're talking about impulse today. Impulse is the change in momentum. Impulse is going to be just a measurement of momentum. How much it changes. Now momentum is mass times velocity. Mass doesn't change. Right? However, velocity will. So if I run into a wall, my mass times my change in velocity, however fast I was going, times, or then whatever my velocity is minus whatever I ended up with, I stop. My change in velocity for most part will be just however fast I'm going, because it's going to stop and go to 0. But impulse is going to be the change in momentum. So the formula for impulse will be, first, from your chemistry class, what's the symbol for the change in?
Delta.
Delta. So instead of using a new letter for impulse, we're not going to use the letter I or anything like that. We just say that delta P, which is the change in momentum, that's impulse right there, delta P, is equal to mass times change in velocity. So if you knew the mass of something, a baseball flies through the air and I'm going to catch it. Okay, it has a mass, it's going 30 meters per second and I'm going to catch it and stop it. How much does the velocity change if it was going 30 meters per second and stops? 30, right? If I want to be nitpicky, I could say negative 30, but I probably won't be. Okay? So the velocity changes 30. Multiply that times the mass and you know it's impulse. That alone is actually kind of boring. But you would be tested on a question like that. What is the impulse of this? You have a mass and a change in velocity. Figure out the impulse. Now, there's actually another formula for impulse, though. When I caught that baseball, I'm going to have to apply a force times a time to stop that baseball. Okay, so the impulse, the mass times the change in velocity that it's going to be acted on the ball to stop it, will be equal to the impulse, the force times the time that I have to apply to it. So the other formula for impulse is force times time. Again, delta P just means impulse. The change in momentum is equal to force times time. All right, I'll let you. Do we pause? We'll pause. Okay. All right. So the big concept though today, the big thing that I want you to understand when you leave today is this. These two have to be equal. The impulse that the ball is going to feel, its mass times change of velocity, will be equal to the impulse that you have to act on it, the force times the time. So yeah, you will have a question on a test. I give you a mass and a velocity, you have to figure out impulse, or I give you a force and a time, you have to figure out impulse. But that's not really that important or useful. It's the fact that they're equal. So mass times change of velocity is equal to force times time. And so it's not just that you have an impulse, but how you catch something. So that baseball comes and I'm going to catch it. I can catch it by just holding my hand out like this and trying to grab it the instant it touches my hand. That's not going to be a lot of time to stop the ball, is it? Okay, if I just do this and the ball hits my hand, that's going to be a very small amount of time. This T right here will be very small. So if I have a very small amount of time and the impulse, no matter what's going to stay the same, I'm going to have a very big force on my hand. And if I have a very big force, either it's really going to hurt me or it's going to bounce out of my hand, or both. But what if I give when the ball comes? So instead of holding my hand out, the instant the ball touches my hand, I'm giving. Okay? I'm going to increase the time it takes to stop. So instead of a very, very small amount of time, 0.00 something seconds, I give. Well, now it's going to be a much bigger time. This T will be bigger. It was the same impulse, it was the same mass times change of velocity, but now the force will go down because the time has gone up. And this is the big key concept that you need to understand today. Okay? The idea is this. If when the time goes up, the force goes down. If you increase the time, you decrease the force. I want you to repeat that with me. If you increase the time, besides Saeed, who was that? Who said it?
Sharon.
All right, let's try it again with everybody. If you increase the time, you decrease the force.
You decrease the force.
If you increase the time, you decrease the force.
You increase the time.
You decrease the force.
Yes, and that's the concept you have to understand today. Okay, so when the time goes up, the force goes down. And you see this especially in sports. You're going to see this all over in sports.
Looks like your whole clothes.
Okay? In sports, a wide receiver will be from the get-go. Every coach is going to tell a wide receiver to practice when the ball comes to give. Okay? And you'll see them practicing. Even in the NFL when they're practicing, they're going to be giving as the ball comes to their hand. A wide receiver isn't going to catch the ball like this. Okay, because if a wide receiver catches like that, there's a very small amount of time, so there's going to be a very large amount of force on the ball and on your hands. So the ball will bounce out. If you increase the time it takes to stop, you're going to decrease the force. The ball won't be dropped. Okay? Soccer, the chest trap. All right? In soccer, when the ball comes to your chest, you don't want to do this, because then the ball bounces off and goes to the other team. So you're told to give, right? When the ball comes to your chest, you're going to give. You're going to increase that stopping time so you have more control. You decrease the force on the ball, it doesn't bounce away, and it falls to your feet. Yes, sir. The force on the object. Okay? I see you. I see you doing that, the Jedi mind trick. I got it. Okay. Any sport, with lacrosse, same thing too, right? When the ball comes, you're not going to hold it out like that, but you're told to give. I mean, any sport, soccer, back to the foot trap. You're not going to just stick your foot out there or it bounces off to somebody else. You're going to be taught to give. Really, any sport will have impulse. And the idea that if you increase the time, you decrease the force. You can even go the opposite direction, not with decreasing the force, but with impulse. If you ever throw something in a sport, you're told to follow through. Because the idea is that you increase the time, you're going to have more impulse. the ball end up going faster. So that's why every sport will be told to follow through when you throw something. If you increase the time, though, you decrease the force, and that's the big concept. All right, what about cars? With cars, where is it that you increase the time and decrease the force?
Break.
All right, brakes. You don't want a car to stop on a dime. You don't want to step on the brakes and the car stops immediately, because then you keep going, or you have a lot of force on your body.
Those are always funny.
Okay, what about anywhere else? When a car accident, where do you want to increase the time and decrease the force?
That's what it is on the road, on the highways, right?
Yeah, let me talk about that in a second. But yeah, what about in your car though?
Acceleration.
Airbags?
Airbags.
Right? An airbag is not designed to inflate and stay inflated. That would be dangerous. An airbag is designed to deflate the instant it's inflated. Because as soon as it inflates, it will be when your head hits it, and you want to bring your head to a slow stop. Okay? If you had an airbag that stayed inflated, you'd hit the airbag, and then it would go the opposite direction.
They still hurt.
So not only would you change your velocity to a stop, you'd have more force going the opposite
I want to
direction.
rewind that so much.
Why would you have more force?
Why would you have more force? Because not only are you changing your velocity to zero, you're going from a velocity to zero back to the other way. You don't want to bounce back, because that just means more force on you. Okay, so that's why an airbag is designed to deflate as your head hits it. Now, one more. Has anyone heard of crumple zones? Your car is designed with crumple zones. The front and the rear of your car are designed to crumple in. They don't want to be built like a tank. Your car, if you had a car built like a tank, that means when you hit something hard or something that wasn't going to move, you would have more force on you. Okay, so a car is designed with crumple zones. The idea is that as you hit something, a wall or a tree, the car will crumple in at the right spot. You'd rather have the hood and the engine all crumpled in than where the passengers are. So we have crumple zones to increase the time to stop and decrease the force on you. If you increase the time, you decrease the force. Okay? Yeah, and back to what you're talking about with on the medians. Like if you see an exit ramp and you see like there's going to be a split with a concrete and all that, you know, or a wall, they will have like those big yellow barrels usually, and that's the idea that you didn't want to hit concrete. So if you have those are usually filled with water or something else, and the idea is that you increase your stopping time if you hit that, and there will be much less damage on you. Okay, they also have even like the guardrails. If you next time you're like at a stoplight, if you look at a guardrail, you'll see the end of the guardrail is designed to look like almost an accordion, so that it can collapse in if somebody hit it head on. All right, again, you want to increase the time and decrease the force. Okay. All right, that is really it. You may stop recording.